Assalamualaikum and a good day to all. So we are going to discuss the last chapter in Physics 2, which is Maxwell Equations. Okay, so before this, we have a lot of theory, which is basically the Ampere's, the Gauss law, but that theory is only done in terms of electric and magnetic field. But now Maxwell are going to show that all electric and magnetic phenomena could be described using only 4 equations involving electric and magnetic field. So this equation we call as a Maxwell equations, okay, which are the basic equation for all electromagnetism. Okay, so now we are going to introduce you with the displacement current. Okay, this is going to be an improvised versions of the Ampere's law. Okay, and then we have the Gauss law from magnetism. So hopefully you still remember the Gauss law for electric field. Before we have the electric flux passing through a closed loop, which is basically this formula. Okay, Q enclosed over epsilon naught, and then we are going to conclude it in 4 equations that going to relate with the electric and magnetic field. Okay, so let's start now. Okay, before I discuss further with displacement current and what does it mean by displacement current here, we are going to recall back about the Ampere's law, which is in topic 9, and changing of the magnetic field induced current electric field, which is in topic 10. Okay, so basically before this, in topic 9, the Ampere's law is about you have a current flow inside the wire. So what happens is this current could actually produce a magnetic field. So when you use the first Thumb's rule, your magnetic field are going to be in the clockwise direction. Okay, so and then in topic 10, we actually discuss about if we have a changing of magnetic flux. Okay, change of magnetic flux, we are going to induce current, which means that when we have a current, definitely we are going to have a electric field, because the electric field is the one that actually do some work to move charge from one point to another point. So that's the reason why for this one we come up with the formula. The change of magnetic flux, okay, the change of magnetic flux induce electric field. Okay, so now we are going to combine both, which means that is there any possibility for the change for the electric field to produce a magnetic field. Okay, but if we have an electric field to produce magnetic field, it's not going to be happen. Okay, because you need to have some changes for you to produce a for you to induce some magnetic field. Therefore, that's the reason why we are going to derive some formula where with the change of electric field are going to produce magnetic field. Okay, because Maxwell's state that if magnetic field can be produced by current, definitely magnetic field can be produced by change of electric field. Okay, okay. Okay, so we are going to discuss first the Ampere's law. Just recall everything back. Okay, so basically when it comes to the Ampere's law, it relates with the magnetic field around a current to the current through a closed surface. Okay, before this, we have a current. Okay, the Ampere's law is basically the formula that we actually create. If example, the wire is not that straight, okay, so we need to find the total. We need to find the net magnetic field over there. That's the reason why we introduce with the formula of the Ampere's law. Okay, so here we have a current, and then we put over there a closed area. Okay, so this closed area we put as a dl, and for us to get the total magnetic field over there, because the B here is basically parallel with the dl, so what happens, we need to integrate for us to find the total magnetic field. So we have this one formula where we put it as Ampere's law, which means that in the closed area, okay, closed loop, okay, B dl, okay, then the permeability of free space multiplied by the I enclosed inside this closed area. Okay, so the Ampere's law is about that. You have a current flowing inside the wire, and then you have a closed area over that, so means that you can actually calculate a net magnetic field. Okay, so basically from here you can actually see that we have surface 1 and then we have a surface 2. Okay, so you can see that when you have a surface 1, okay, and then we have a current which is enclosed inside the closed loop, so definitely surface 1 can produce a current. Okay, and basically we can actually use an Ampere's law. But what about surface 2? Okay, surface 2 also is basically a closed area, which basically if you have a current inside, you can actually calculate the net magnetic field over there. Okay, so here the current we are going to change into, okay, so what if we change the current here into capacitor plate? Okay, so as you can see that for the capacitor plate, there's no charge flow between the plate. Okay, if not, there will be a short circuit. Okay, so we are going to investigate whether this capacitor plate can actually use the Ampere's law formula. Okay, like I mentioned before, the Ampere's law is about current enclosed inside enclosed inside the closed area. So basically for the surface 1, this one are going to obey the Ampere's law, because as you can see that you have a current here, okay, and then you have a closed area, or we call it as a closed loop. So this one can actually use the Ampere's law formula, where it's going to be BDL, okay, the closed area equals to mu naught I enclosed. Surface 1 doesn't have any problem, but what about surface 2? Okay, as you can see that, like I mentioned before, the only current that can be used for the capacitor is AC, not DC. Okay, and then the charge cannot flow in between the plate. So basically, if there's no charge flow between the plate, definitely there will be no current. Definitely there will be no current flow between the plate. So means that this part for the surface 2 cannot use the Ampere's law. However, as you can see that, okay, the electric field flow from positive to negative. Okay, the conventional current flow is going to be from positive plate into the negative plate. Okay, so basically what happened here is the electric field over there, like I mentioned before, if you have a current, definitely you are going to have an electric field. Okay, because current flow from positive to negative, electric field also flow from positive to negative. Okay, so it means that if you have a current, you are going to have an electric field, which means that definitely you are going to have a magnetic field. But the problem here is there's no I enclosed for surface 2, because there's no charge flow between the plate. That's the reason why we need to improvise the formula, because the problem now we can actually produce magnetic field. But for the surface 2, there are no current enclosed inside the surface 2. Okay, so how to improvise the formula? Okay, so you can see that for this right side part, we are going to add another part to make sure that even though there's no current inside the closed area, if there's a change of electric field, it also can produce a magnetic field. Okay, so how to get the formula? Okay, so first thing first, when it comes to the electric field, the first thing that comes in your mind is the charge. Okay, charge leaving the plate, charge enter the plate. So we have here is Q equals to CV. Okay, so you have two plate, okay, which is basically very, very close, okay, and then you have an electric field flow between the plate. Okay, example, this is positive, this is negative, so it's going to flow like this. Okay, and then we assume that the electric field in between the plate is uniform, which means that we ignore any fringing of the field, okay, because it's very, very close. Okay, here definitely we are going to have a potential difference between the plate, so we recall the formula, which is going to be V equals to ED. Okay, and then if you remember, we have this one formula to relate the capacitance with the area of the plate, epsilon naught, and the distance between two plates. Okay, so we are going to combine this formula. So we have Q equals to CV. We put C into this formula. We put V into this formula. So we are going to get A epsilon naught over D equals to ED. So we are going to cancel the D. So we are going to get Q equals to A epsilon naught E. Okay. So as you can see that the charge enter and leave in the plate. So basically, charge always change at the rate of dq over dt. Okay, because the charge always leaving and enter the plate. So basically what happens is the charge are going to change at the rate of dq over dt. Okay, which means that I can actually say that if the charge change at the rate dq over dt, the electric field also change at the same rate. Okay, the electric field also change at the same rate with the charge. Okay, so here dq over dt equals to, okay, we are going to get this formula as A epsilon naught dE over dt. Like I mentioned before, the charge change at the rate of dq over dt, which means that the electric field also change at the same rate. Okay, and then dq over dt is what? Current, right? Okay, so here, if you still remember, we have electric flux, which is basically EA. So I'm going to so right now we are going to do some little bit changes here, which is dq over dt, which is basically a current, equals to epsilon naught d flux E over dt. Here. Okay. So here we call it as the electric flux. Okay. Pass through the closed path. Okay. Pass through the closed path. Okay. So here we are going to put dq over dt is basically a current, which, like I mentioned before, if you have current flow inside the wire, you are going to produce an electric field. You are going to produce a magnetic field. So here is going to be a current, which means that the change of electric field or change of electric flux also produce a magnetic field. Okay. So the new formula for the Ampere's law, which we are going to embody the Maxwell idea over there, is going to be BDL is going to be magnetic field are going to be produced by, okay, first the I enclosed inside the closed area plus mu naught. We need to multiply the permeability of free space because the area between the two plates, mostly for the Maxwell idea, is in free space. That's the reason why we need to multiply with the permeability of the free space. Okay, equals to, we are going to take this one, d flux E over dt, which means that here we are going to state that the change of the current can actually produce magnetic field. At the same time, the change of electric field also produce a magnetic field. And this is basically Ampere's law, and we embody the Maxwell idea. The magnetic field can be caused not only by ordinary current, which is this one, but also by the change of electric field or electric flux. Okay, so we already have one formula from the Maxwell formula. Okay, okay, so here we have a questions for us to apply back all the concept. Okay, so now the question asks you to find A, B, and C. Okay, a 30 picofarad air gap capacitor has circular plates of area A equals to 100 centimeter square. It is charged by 70-volt battery through a 20 ohms resistor. At the instant the battery is connected, the electric field between the plate is changing. So once we got this information where the electric field is changing, it means that it's going to produce a magnetic field. Yes, great. Okay. At this instant, calculate the current into the plate. Okay, so this diagram is basically one face of the plate. Okay, so here you are going to have electric field which is pointing out of the page. Okay, and then please take note the directions of electric field is basically the same as directions of current, conventional current. So you can use the first thumbs rule. Okay, so when you use the first thumbs rule, you are going to get your magnetic field moving in anti-clockwise. Okay. So but the question asks you to find the current into the plate. So it's practically very easy. Okay, so we have a 70-volt battery and then we have the 20 ohm resistor. Okay, so basically you can just use V equals to IR, but the question is about charging capacitor. So charging capacitor, you have a formula. Q equals to Q max 1 minus E negative T over RC. Okay, recall back the formula. Okay, so the Q max is basically CV naught. Okay, so for us to find the current, at T equals to 0, we are going to differentiate because we have dq over dt, which is basically a current. So we are going to get this one, the derivations of this one, we are going to get CV naught over RC E negative T over RC. So you are going to get V naught over R. So here E going to be 1 because at the T equals to 0. So you are going to get I equals to V equals to IR. Okay, the reason is I show you this formula because we are going to relate with the charging capacitor. If we only use V equals to IR, we assume there's a resistor over there. And in this picture, doesn't have any resistor. So you need to show how to get this formula up until you get V equals to IR. Okay, so you are going to get the answer, which is 35 ampere. Okay, the rate of change of electric field between the plates. Right now, the question asks you to find the rate of change, which is dE over dt. Okay, so it means that okay, what is the formula for two plates which have the separation very small and the dimension of the area very large? It's going to be E equals to sigma over epsilon naught. So this sigma is basically charge per unit area. Okay, so the question states about the rate of change of electric field, which means that you need to find the dE over dt, and like I mentioned before, change of charge are going to be equal to the change of electric field. So in this one, we are going to dq over dt a epsilon naught, which means that here dq over dt is what? Current. So you are going to take the current from the first question. So it's going to be I a epsilon naught. That's how you get the formula. So you are going to get the answer is 4.0 power of 14 volt meter per second. Okay, for the next question, which is determine the magnetic field induced between the plate. Okay, determine the magnetic field induced between the plate. Okay, this one I'm going to show you with different conditions. Okay, and then I'm going to use this picture as my reference. Okay, so let's start. Okay, so I'm going to use this picture as my reference. Okay, first thing first, we are going to find the magnetic field induced, okay, because of the change of electric field. Okay, change of electric field with three conditions, which is one is going to be R less than R naught. Okay, the R naught is the full radius of the circle, and the R is the one that we need to find, the area, the enclosed area that we need to find. Okay, so after that we are going for the R more than R naught and the R equals to R naught. Okay, so I'm going to start with the R less than R naught. Okay, so basically here the original formula, the Ampere's law that we modify with the Maxwell idea over there, is going to be B dl mu naught I enclosed plus mu naught epsilon naught d flux E over dt. But this one going to be 0 because here there is no current enclosed inside the area. The only one that have is a change of electric field. So we are going to get the only formula is B dl equals to mu naught epsilon naught d flux E over dt. Okay, so here, this is the enclosed area, which the one that you need to find. Okay, and this one, inside this formula we have a dE over dt. The area here is going to be the area that only have a change of electric field. Okay, please take note, the area here is the area that have a change of electric field. Okay, so here, because we choose a circle shape and then circle shape over here, so we are going to have a uniform magnetic field. Okay, a uniform magnetic field. So it's going to be B enclosed dl equals to mu naught epsilon naught A dE over dt. Okay, so this one you are going to get 2 pi r. The L here, the dl here is the enclosed area that you need to find. Okay, mu naught epsilon naught, and the area here is basically to represent the area that have a change of electric field. So basically, if you use R up until here, you can see that here still have a change of electric field. So we are going to take that pipe only. Okay, so it's going to be is going to be pi r square dE over dt. So this one can be cancelled, this one can be cancelled. So you are going to get your magnetic field induced is mu naught epsilon naught over 2 r dE over dt. Okay, that is going to be our formula for R less than R naught. Okay, right now we are going to derive for the next one, which is R more than R naught. Okay, R more than R naught. Okay, so R more than R naught. Okay, so here the enclosed area already changed, which means that you have this area which you have a change of electric field. Okay, and then you have area R which is more than R naught here. Okay, so we are going to use this formula, and then the I enclosed is still 0 because there's no current enclosed inside the closed area. So we are going to get B dl equals to mu naught epsilon naught d flux E over dt. Okay, because it's circular plate, so we are going to have a uniform electric field. So here is going to be 2 pi r. Okay, because it's the area that we need to find, equals to mu naught epsilon naught area dE over dt. Okay, so B equals to 2 pi r mu naught epsilon naught. Area here, like I mentioned before, is the area that have only change of electric field. So basically, the only one that have a change of electric field is only up to this pipe. okay, which is up until R naught. So means that here your formula are going to be pi R naught square dE over dt. Okay, so pi can be cancelled out, so you are going to get your induced magnetic field is mu naught epsilon naught over 2 R naught square dE over dt. Okay, if we have R equals to R naught, so you can actually use only this formula, which means you are going to get the same thing, which is going to be B equals to mu naught epsilon naught R naught over 2 dE over dt. Okay. But here I'm going to show that for the R larger than R naught, you are going to get the same formula that like the previous one that you get, which is B equals to mu naught over a mu naught B equals to a mu naught I over 2 pi R. Okay, so here only for this part, only R for R more than R naught. Okay, so we have because we need to find the B outside the plate. Supposedly we are going to get the same formula like the previous one that we actually get. So we are going to put here like E equals to sigma, E equals to sigma over epsilon naught, which is Q A epsilon naught. Okay, so if we have dE over dt, we are going to get dQ over dt A epsilon naught, which means that is going to be I over A epsilon naught. Okay, so I need to shrink this a little bit. Okay, so you put this back into this formula. Okay, you're going to put back into this formula, so you are going to get it is going to be B equals to mu naught epsilon naught R naught square over 2R, okay, I over A epsilon naught. Okay, so epsilon naught can be cancelled out. Okay, the area here is pi R naught square. Okay, because that's the only area that have a change of electric field, so the R naught here can be cancelled out. So you are going to get the formula is, when you rearrange, B equals to mu naught over 2 pi I over R. Okay, I think you are very familiar with this formula. This is like the previous formula in chapter 9. Okay, so when you have a current flow inside the wire, you are going to have a magnetic field, and this is basically the formula for you to calculate the magnitude of the magnetic field. Okay, so in other words, we can actually say that the magnetic field produced by the changing of electric field between the plate is the same as that produced by the current in the wire. Okay, so because this formula is basically derived from the change of electric field, so we basically get the same formula when the magnetic field produced by the current in the wire. Okay, that's how you get the formula. Okay, so we are going to simplify a little bit the Ampere's law embodied by the Maxwell, which we call the one that we find is the displacement current. Okay, so the one that you find from the previous one, which is this is the formula. Okay, mu naught I enclosed plus mu naught epsilon naught d flux E over dt. Okay, for this part we call as a conventional current flow. Basically here we call another name is a conduction current. Conduction current. Okay. And then for this one, we call as a displacement current. So basically what happened here is we assume that when you have an electric field passing through between the plate, as if you have a current passing through between the plates. Okay. So that's why we assume that this part is a displacement current. Okay. So when we have a formula, we need to change a little bit formulas. We are going to get BDL, the Ampere's law, with the Maxwell idea over there, going to be mu naught. This is going to be I conduction current, which is the current enclosed inside the closed area, plus with the displacement current. Okay. So this is the way for you to write the formula. Okay. So you need to understand also that, okay, so we need to imagine that, okay, the conduction current conduction current can only be flow up until this part only. Okay, this is basically the one for the conduction current. But no conduction current basically flow in between the plate. Instead, a displacement current flows out at one of the plates. So basically here is going to be your displacement current, because conduction current cannot flow between the plate. There's no charge flow between the plate. If not, there will be a short circuit. Okay, so as if that the change of electric field is basically a displacement current flows out from one of these plate. Okay. So if Ampere's law the whole, okay, because right now we already changed the formulas, so basically both formula obeys the Ampere's law. There must be a magnetic field generated by the changing of electric field between the plane. Okay, so the induced magnetic field that produced by the changing of electric field looks like there's a current which we call as a displacement current passing through the plate, as if you have a current passing through the plate. Okay, so means that you can actually see that from this picture, okay, with the change of electric field, you are going to have a induced magnetic field. So basically here is going to be the area for the conduction currents, but the conduction current cannot flow between the plate, but the one that leaving the plate is going to be displacement current. Okay, which means that the formula for displacement current only is basically displacement is absolute naught d flux E over dt. And here, because of change of electric field or change of electric flux, going to produce a magnetic field. Okay, got it? Okay, so we finished with that first part, first formula from the Maxwell equations. Okay, so now we are going to discuss about Gauss law from magnetism, but before that, we recall back about Gauss law for electric. Okay, so when you have a charge, example, you have positive charge, positive Q over there, okay, and then you have a Gaussian surface here. Okay, this is your Gaussian surface. Okay, and then we have electric flux, which means that how many electric field passing through a given area, and our area is a Gaussian surface, means that we can actually use the formula for Gauss law, which is enclosed volume. Okay, Ampere's law is about closed area, Gauss law is about enclosed volume, equals to EdA, which is electric flux, equals to Q enclosed over epsilon naught. So basically for this one, you have Q inside the Gaussian surface, therefore you are going to put here as a positive Q over epsilon naught. Okay, but if you have positive charge and negative charge, and then you put it inside one Gaussian surface, is there any electric field? Or electric field basically zero or not? Is going to be zero, because for the Q enclosed, plus Q minus Q over epsilon naught, you are going to get 0. Okay, because positive end up in the negative like that. Okay. So Maxwell proposed, if we have a Gauss law for electric, definitely we are going to have a Gauss law for magnetism. So we are going to change a little bit formula. So we are going to get not electric field, we are going to get BdA, which is flux for magnetic field, equals to Q enclosed over epsilon naught. But the problem here is magnetic field doesn't exist in monopole. Okay, like charge, we discussed about electric field. Okay, charge and electric field relate so much. But when it comes to magnetic field, okay, you have one magnet, we have north and south. Okay, there's no magnet that monopole, or we can call as a one pole. Okay, magnet always come in north and south. Okay, and then you can see that the directions of magnetic field going to be closed loop. Okay, it's not going to like end up, it's not going to be like charge where you have a positive charge and then it's going to stop at negative charge. Okay, and then charge can be isolated, means that it can be like one charge, one positive charge inside the Gaussian surface or one negative charge inside the Gaussian surface. However, when it comes to magnet always come in north and south, which means it's going to be from north and end up, not going to be end up, it's going to be in closed loop and always be continuous. Okay, always be continuous, which means that here is equal to 0, because we can actually assume like north is a positive, south is negative. So when you put it inside the Gaussian surface, you are going to get what? 0. Because it's always continuous, always in closed loop, the magnetic field. Okay, and that's the reason why you are going to get the formula for the Gauss law from magnetism is BdL equals to 0, which means that the magnet not comes, there's no magnetic monopoles, always be north and south, and always be continuous and in the closed loop. Okay, okay. There is the formula for Gauss law for magnetism. Okay, and then you can actually see that even for a bar magnet, a magnetic field exists inside here, exists inside the magnet, and also exists at the outside magnet, which means that it's always be in a closed loop. Okay. Okay, so here is the evidence of, you can actually see that the north always start from north, and then is always in continuous, and then is going to enter in from the south, and that's the reason why you are going to get here equals to 0. Okay. Okay, so basically this one, okay, okay, when it comes, okay, this is the Ampere's law for magnetic field. Okay, which means that here, okay, we need to improvise a little bit this formula, where we are going to get mu naught epsilon naught d flux E over dt. Okay, so basically this is the for the closed surface one, where is obey the Ampere's law because there's a current flow inside the closed area. And here we can actually state that we have displacement current, as if we have a displacement current. Okay, which means that the magnetic field is basically produced by the change of change of electric flux or change of electric field. Okay, Ampere's law is about closed area. However, when it comes to the Gauss law, it's about the enclosed volume. However, like I mentioned before, magnet doesn't come, there's no magnetic monopole, always be like north and south together, and that's the reason why you're going to get BdL in the enclosed volume equals to 0. Okay, so now we are going to conclude the equations. So basically the four formula that the Maxwell equations state here, this one is for okay, the Gauss law for electric. for electric, which means that is going to relate with the charge that enclosed inside the Gaussian surface. And the charge can be isolated. It can becomes like in one charge, like you have one positive charge inside the Gaussian surface or one negative charge inside the Gaussian surface. Okay, but however, when it comes to the Gauss law for magnetism, okay, this is Gauss law for magnetic. Okay, there's no magnetic monopole. Magnetic field line always continuous, and they do not begin or end like electric field lines do on charge. Okay, like electric field can like start from positive charge or end up on the negative charge. Okay, and this one is a formula where the change of magnetic flux induce electric field. Okay, and because of this one, we try to relate that why not the change of electric field can actually induce a magnetic field, and that's the reason why we come up with the fourth formula, which is the Ampere's law. And then we put the Maxwell idea over there, where a magnetic field can be produced by a normal electric current or by the change of electric flux or electric field. Okay, and that is the fourth formula for the Maxwell equations. Okay, so now we have only like quick quiz. Okay, this is a very simple quiz. Okay, in RC circuit, okay, because we before this we discussed about capacitor. Okay, the capacitor begins to discharge, okay, during the discharge in the region of space between the plates of capacitor. The question states between the plates of capacitor there is, okay, so the space between the plate of capacitor, there will be no current flow, okay, but there will be an electric field passing through between the plate, which means that the change of electric field going to produce displacement current, but there will be no conduction current. Okay, no conduction current cannot flow between the plates. If not, there will be a short circuit. Quick quiz 2. The capacitor in RC circuit begins to discharge also during the discharge in the region of space between the plate of capacitor. So the question states, in the region of space between the plates of the capacitor, there is this. They are going to have both electric field and magnetic field, because now we are going to talk about the change of electric field are going to produce a magnetic field, and that's the reason why you are going to get answer C. Okay, so the last questions are going to be the last part in this slide, which means that we already comes to the end for the chapter 14. Okay, so we are going to do some questions tomorrow. Okay, but please make sure that you fully understand what does it mean by Maxwell. It's very short topic. Okay, and then that means that we already finished all the topics in phases 2. Okay, so thank you very much for your attentions, and hopefully all the video are going to help you in terms of the understanding. But if you didn't understand, you feel there's something that you need to clarify with me, feel free to ask. Okay, so thank you very much, and assalamualaikum. Bye bye.